You're welcome to the first session for Business Mathematics, Ugbs 202. I'll take you through a number of mathematical, let's say, operations which we'll need for this course. This first session is going to be basically on some introductory aspects of calculus. Okay, so just hold on tight with me and let's go through some basic stuff. Well, very important things in calculus more times are centered around issues like limits and differentiations and integration. Well, we wouldn't get too deep into those topics or those issues, but we'll do them just for you to have some basic ideas, because we are going to borrow these techniques into our typical business activities, right? And so my first slide here, I have something we say derivative of a function. When we say a derivative just tells us the slope, or gives us an idea of how we are able to find that instantaneous rate of change of a function. And so normally if you want to find the slope of, say, a straight line, we know that you basically will just use the rise over run. You pick two coordinates on a straight line, your x coordinates and then your y coordinates. And then you take the y coordinates, y2 minus y1 over x2 minus x1. That is easy. But well, with regards to calculus, we normally would, how about you want to consider the case of finding the slope of a curve, a point on a curve. That wouldn't be that easy as we normally would find it back in, let's say, algebra. So that's what basically calculus actually does. In fact, like this issue of differentiation. On my slide here, let's see this simple graph here. I have a graph here. And I just want to walk you through how we can easily find the slope, or what we call the gradient of a point on this graph. It is not that easy in the case of basic algebra, where we could just actually do our rise over run here. Well, we would definitely need 2 points to actually find the slope. That one, no two ways about it. Okay, so let's say I pick this point. I am interested in this point. I call it point A. And if you see something here, my f into bracket A, that's what we call a functional notation, right? It's just a fancy way of rewriting this same point A here. It's nothing extraordinary. Now, I pick this point. I am interested in finding the slope of this point. But to find a slope, like I said, we need 2 points. And so let's say I pick another point here, Q. I draw a straight line, which I call PQ. Now, this straight line actually connects these 2 points that I'll need for my slope. And I think back in high school, you can see that the name of this straight line, we'll call it a secant line, a line that connects 2 points on a curve here. Good. So if I have these 2 points, I think I am almost there to find my slope. So here, what I do is, see, from this point, I can now get my second coordinate here. So let's say PQ, point A here, and then between this horizontal distance from this point to this point, which corresponds to my other point Q here, would be my second point. The distance between P and, okay, so let's say the distance between A and Z, I'll call it H. Just H to stand for horizontal distance, H for the word horizontal. And so I just put these together. And so my second point, I'll call it Z here. And then the other case, the same functional notation here, I write it f of Z or f of Z. I put these together, I'll have my x1 coordinates and x2 coordinates, y1 coordinates and y2 coordinates, just the same as we do for finding the normal slope of a straight line. Now, what I am really interested in is the slope at this point, not for this straight line. And so there's this basic idea we call limits in calculus. In fact, it's pre-calculus. You do this before you even start the whole idea of differentiation. What this idea just tells me is, well, you see, this is going to be an estimate of the slope here. But the estimate could get better and better if I reduce this horizontal distance here. And so the flatter I make my straight line or my secant line, the better the estimation for the gradient point here at point P. Well, with all this, we'll move forward to, well, in differentiation, we'll call it the first principles in differentiation, where we say we can have our f of a plus h minus f of x over h, basic stuff, but we'll see them when we move forward. So now let's look at the main idea I'm trying to put across, differentiation. Well, differentiation is a mathematical principle, like I said, that we use to find the slope or the gradient of a curve. There are some basic rules that we adopt or we use in differentiation. In fact, you only need them. They are not difficult. They're not any extraordinary rules that you need to do differentiation. The only problem is, well, you can actually use them, but as to when you use them is the big deal. And I'm sure we'll get through them and there wouldn't be any big problem. So the first rule, which is the simplest or the easiest of all, is what we call the constant function rule, which says that if you have a constant, and a constant is just any absolute number, let's say 4, 5, but any number, even if it's 1 million. So for us, it does not carry any variable. We refer to it as a constant. It's not a function. If you want to differentiate a constant, the answer is 0, or the differential there is 0. And so you see, if I have, let's say, this notation here, dy dx, this is just saying I am finding the differential of a certain function with respect to x. So supposing I have a function, say y equals f of x. So y is composed of f of x, or let's say x is a function of y. Then if I want to find the differential of y, I can write this as, say, f prime, or say dy dx equals 0. That is if what I am differentiating is a constant. And so it is just basic. Well, there are mathematical proofs to show this, but I don't think this is a math class, so we would not get too much into it. The other one here is the power function rule. If you have a function that has certain exponents, let's say, like I have here, let's say y equals x to the power n. If I want to differentiate a function as that, it's a basic rule. It says that take the power of the function, bring it to the front of the variable or the function, and then knock down the power by 1 or reduce the power by 1. And so look here, I have a function here, 4x to the power 4. Now, this is my function. The differential of 4x to the power 4 would be, see, I take the power here, 4, I bring it to the front. So kind of like you just take the exact power, just that exponent, bring it to the front of the whatever is before the function, and just reduce the main power by 1. And so what I do there is, well, here, let's see it. I have 4x to the power 4. Actually, this should be 4 times 4 by x. Then I reduce the power by 1. And so I have that to the power 3. Okay, now, so take this. Yeah, so it goes on and on and on and on like that, and it's nothing extraordinary. So look at this. The differential of 4x to the power 4 is 4x to the power 3. I take this. This is the power 4. I bring it to the front of the variable x, and I reduce the power by 1, and it becomes the power 3. Okay. Now, the third rule we'll also look at is the generalized power function rule. Now, this is more like a little build up on what we just saw. It's still the same idea of bringing the power to the front and reducing it by 1. But this one, let's say my function actually does carry some constant before the variable or before the entire function. And so, for instance, it says that here, if I have a function, say f equals c times x to the power n, where c is, let's say, my constant, xn is the function. I take my n, multiply it by the c, and just reduce that same n by 1. And so, for instance, let's say we have 5x to the third. What I'm going to have here is, I'm going to have my power, which is 3. I bring 3 to the front, so that is 3 times 5. And then I reduce the power 3 by 1. So what I have now is 15x squared. Okay, so it goes on and on and on like that. So Good. Now let's look at some other rules, but this time around we want to see, let's say, some functions that have more than one variable. We're not getting into other parts yet, but this is just basic stuff. So for instance, supposing I have a function, say f of x plus or minus g of x. Let's say I have two different functions that are being joined by some binary operations, let's say either addition or subtraction. It is just the same thing that we do, just differentiate it as we spoke of it before. And so it's just going to be my f prime x plus what? G prime of x. Now, when I mean prime, this f prime of x is just saying that this is the differential of the function f, and g prime of x is the differential of the function g. So let's take a numerical example and see. Supposing that I have a function y equals 3x squared plus 2x squared plus x. Now you see, this is a function on its own, this is another function, and this is again another function. All I'm saying is take these functions individually, differentiate them just as we've discussed, and just put them together or join them together with the binary operation here. Here, the sign we have is plus. So now, the first one is 3x squared. You can just use the same generalized power function rule, which says that take the power, multiply it by what is in front of the function, and then reduce the power by 1. And here, so what do I have? If I have 3x cubed, 3 times 3 is 9. 3 minus 1 is 2. So what I have here is 9x squared. Now I move to the second function, which says 2x squared. I do the same and I have 4x. Now x, well, x is just a function. It's just a variable. But you do know that x, it has an invincible exponent, which is more like 1, right? And you know any number raised to the power 0, basic mathematics is 1, isn't it? So supposing that I do 1 minus 1, the power of x becomes 0. And what do I have here? I have 1, right? So it's just a basic something. Okay, so let's see. Well, like I said from the beginning, what we are doing here is we are not actually doing mathematics. We are doing business mathematics. So what we are doing is just borrowing these mathematical principles into business perspectives. So after all these, what's it called, introductions, we are basically going to rather apply them in business cases. And so let's just take a tip of the iceberg, more like a little example in business sense. Now, for instance, if I have a total cost function, and I'm sure we are all familiar with these cost structures, total cost of, let's say, producing a certain number of outputs, which says Q3, or Q to the power 3, minus 4Q squared, plus 10Q, plus 75. Now, this is a cost function, a total cost function. Supposing that I ask you to find the marginal cost function, which is more like the slope of the entire cost function, then all I'm just asking you is to differentiate this function and just give me the derivative. Very easy. Okay, so here, I think by now we all can do this. But let's go through it. This is Q cubed. So I take the power, which is 3, I bring it before the Q. Right? Now I have 3Q. Then what do? I reduce the power by 1. So I now have 3Q squared. The second function here is 4Q squared. 4Q squared is, well, it turns out to be 8Q. Now, 10Q. This Q has a power of 1. So once I reduce it, I have 1. Now look at this interesting guy. This guy is 75. 75, like we said, is a constant. It carries no variable. Right? And so if I differentiate the constant, what happens? It drops dead. It's 0. So it's gone. So this is going to be my marginal cost function or my derivative of this cost function. Okay. Now let's move on to some rules that are just a little bit, let's say a little add-ons to what we've just seen so far. We'll call this one the product rule of differentiation. Now, the product rule says that if you have a certain function, let's say f of x times g of x, then if you want to find the derivative of a function as this, like two different functions multiplying each other, all it's just saying is take the first function, leave it as it is, multiply it by the derivative of the second function, which is g prime of x, and then join them with whatever sign, whether it's plus or minus. But well, this case, it is just going to be plus, because for product multiplication, it turns out to be addition here. Okay, so then do just the reverse of what you did in the first instance. In the first instance, I said, take the first function, leave it as it is, multiply it by the derivative of the second function, then add it to the original second function, and multiply that one by the derivative of the second function. Let's take an example. All right, so let's take an example of the product rule. So let's say I have a function 2x squared plus 4 being multiplied by 6x cubed plus x squared. Okay, the rule says that these two functions, let me call this my f of x and I'll call this my g of x. Okay, now the rule says that take f of x as it is, multiply it by the derivative of g of x, then add it to, this time do the reverse, keep g of x as it is and multiply it by derivative of f of x. Right? Okay, so let's go. Now, supposing I have this function, this is my f of x, so I'll keep it as it is, 2x squared plus 4. Okay, sorry about that. 2x squared plus 4. So you see, I keep this function as this. Now, I'll differentiate this function. Now, this function here, 6x squared, 3 times 6 would be 18, isn't it? And then 3 minus 1, so this is going to be times 18x to the second power, right? And then here, x squared, I would have 2x. That's it. So I'm done with this first part, which says I keep my f of x as it is, and then I multiply it by the differential of my g of x. Then it says I add it to, I'll now do the reverse. So now I keep my 6x cubed plus x squared, then I multiply it by the differential of f of x. Now f of x here is 2x squared, so I multiply this 2 by this, and what do I have? I have 4. Then I reduce this by 1, so now I'm going to have 4x. See it? Now this is a constant, so if I differentiate it, it goes away, and that's it. You're done. Right? But well, because it's mathematics, math is supposed to make life as simple as possible. And so, well, in as much as I don't have a problem with this being the solution, you can again just break this down a little bit by just multiplying and distributing and just probably try to factorize it and make it a little bit more easier, right? But in any case, if you leave it like this, you're equally correct. Okay. All right. So that was the product rule. Now let's look at another one, the quotient rule. Well, when you talk of quotient, it's just like saying division. Okay, so, well, the quotient rule says that if you have two functions trying to, let's say, written in the form where one is on top of the other, or probably looking like something like this. This is one function being divided by this function. It is a very simple rule. It says that just like we were doing before, it takes a little bit of the product rule and then adds a little tweak to it, and it just gives you a very awesome rule. It says that take the lower function, so the function beneath, or what the denominator, I'll label that as my g of x, and then the numerator will be our f of x. Take your denominator, keep it as it is, do not do anything to it as at yet, and then multiply it by the differential of the numerator. Then subtract it from, keep the numerator this time around, and then this time multiply it by the differential of the denominator. And then let's say you divide by the square of the denominator. In fact, this is very easy. You can have a basic mnemonic for it. You see, let's call the one beneath, the one at the top, which is the numerator, the high term, and then this one, the denominator, as the low term. So how about you say low d high minus high d low over low low. You see, it's basic, isn't it? This is my low term. Then I multiply it by the differential, which is d high, just like we say dy, dx kind of stuff. Yeah, so low d high minus high d low all over low low. Low low is the square of a function. It's multiplying itself. You see it. So I guess you can try this. So just take this function, leave it as it is, 2x minus 1. Do not do anything to it yet. Then multiply it by the differential of this. If I take the differential of this, it is just going to be 8x. So all I'm going to have at the first instance is 2x minus 1 multiplied by 8x. Then I do minus. This time I keep 4x squared plus 3. I do not do anything to it. And then I multiply it by 2. And then all I do is to divide by 2x minus 1 squared. And you can just expand that, and that is going to be easy for you. And once you do that as well, you are equally done. You don't necessarily have to do, but, well, preferably, or let's say ideally, it wouldn't be bad if you just broke it down a little bit to some smaller term. Okay. So this is a good friend here. In fact, one of the very important rules in differentiation. We call it the chain rule. In fact, the chain rule is awesome. It's one of the best you can have, because we are going to keep using it over and over and over again. Good. Now, the chain rule helps us to deal with certain functions that we cannot easily deal with. Now, or let me put it in a better perspective. The chain rule actually deals with or helps us solve problems that the other rules cannot easily solve. You know, normally we call the kind of functions that we use the chain rule for as composite functions or compositions of functions. Now, for instance, take a function as this. You see, this is x squared minus 1 into bracket to the power 7. Now, you see, this is a function on its own. This is another function. So it's like a function within a function. Is that okay? But it is basic. Using the chain rule, it is just a simple thing. It says that you would want to simplify the thing as much as possible. So I'm going to teach you two approaches of dealing with the chain rule. One, a very straightforward approach, and the other one, we'll call it the U substitution, which is also an idea used in integration there. But here, supposing that I want to deal with this function. You see, this is x cubed minus 1 to the 7th power. This is a function on its own. This is another function on its own. What do? Let's assume that this function does not exist. Assume that x cubed minus 1 does not exist. And let me deal with this exponent here. So if I assume this function doesn't exist, it is just going to be like, say, a variable with a certain power. Right? So supposing I use a variable, say u. Well, in theory, I don't know why we normally use u. So we just also keep to the convention. So supposing I represent this entire function x cubed minus 1 with the alphabet u, what I'll have here will now be u to the power 7. Now, when you have a simple function as u to the power 7, I think it doesn't get any better than this, isn't it? So all you use is your power rule and you're done. So if I have a function as this, I represent this entire something, just like cover it up, it doesn't exist. I have something to the power 7. I take the power, bring it to the front, and then reduce the remaining with 1. And then what is the next thing you do is just back substitute. So this is how I did it. So I said let x cubed minus 1 be equal to u. You see? So I have represented the inner function, which is x cubed minus 1, to be u. So this is what I have. Now, once I have this, the entire function now looks like u to the 7th, or u to the power 7. Now, what do? If I have u to the power 7, I just deal with it like a normal power rule function. And so I bring it down. So I now have u, which is my 7. I bring it here before the u. And then I reduce the 7 by 1. So what do I have? 7u to the power 6. I hope you understand. Good. Now, when you have this, well, the function wasn't given to you in u. It was given to you in x. So what do? You back substitute. And so rewrite u as it was. So what was u? I said u was equal to x to the 3rd power minus 1. So what do I have here? I have x to the 3rd minus 1 to the power 6. That's it. That's the first part. I've done that's just the let's say, the cracking part of it. The rest of it is just says that, you see, the rule says because it's dy dx, you should do dy du and then du dx. What I have done now is I've done my dy du, which is this, because I represented the entire function with u. So y equals this. So what I'm doing, the rest I'm going to do is just to find the differential of the inner function, which is x cubed minus 1. And then I'll multiply it with what I just did with the back substitution, and then you're done. So here, if I differentiated x cubed minus 1, this is going to be 3x to what? The second power, because I take the 3, bring it to the front, and I subtract 1. Now, if I differentiate this 1, it's a constant. It goes away, and it becomes 0. So all I have is 3. So look at the rule. It says dy dx equals dy du times du dx. Okay, so this is my u. My inner function, I represent it with u. Now, if u equals this, I just differentiate x with respect to u. Is that okay? So this is what I have. So this is du dx, sorry, and that's what I have. Now I take my dy du, this is it, 7u, and so I just back substitute and you're done, right? Now the simpler way of doing it is just say, well, I wouldn't call it a simpler way, more like a straightforward way. Well, because we're students, for exam purposes, any examiner would want to see all these approaches. But just for you to have a better understanding, I can say we'll do it this way, just straightforward. It's like, say, once you identify your inner function, differentiate your inner function, and just say, like I said, cover it and assume that it wasn't there. You have your power function. Just do the same, back substitute and multiply. Straightforward. Okay, so this is what I was saying. Now, take my question here. Now, I am saying that, supposing, all I just want you to do is, if I covered this portion of the question, supposing this wasn't there, what you're going to have is, let's say, a certain bracket with a power, isn't it? Now, all I'm just saying is, I take this 7, I bring it to the front, and then what do? I reduce this by 1, isn't it? Good. Now, this is, say, I kind of represent this entire thing with you. I am done with the first aspect, right? But the rule says, you see, once you have this, take the outer function, deal with the outer function, and multiply it with the inner function, okay? So this is my outer function. This is my inner function. What is my inner function? I'll take the differential of my inner function, which is 3x cubed, sorry, x cubed minus 1. What do I have here? I have 3x squared. You're done. That's just it. Straightforward. See, but the only difference here is, well, my function wasn't written in u, and so I back substitute and I say, well, just like x cubed minus 1 to the sixth power. Is that okay? And again, you can also maybe reduce this. But, well, if you're not too mathematically inclined and you've been able to successfully get to this place, I think you can just leave it here and you're good to go. Otherwise, you can equally break this down, probably do some multiplication, take this function here, and, well, but even if you leave it this way, you're still correct. It wouldn't hurt. Okay, so let's look at some concluding aspects. There are certain special functions in differentiation, like where we can also differentiate logarithmic functions and other things. But let's look at this interesting one here. Supposing you have a function, say y equals ln of x. This ln here is just representing the natural log. So we say, supposing we're taking the natural log of a certain function, say x. How would we deal with an instance like that? Now, so again, we will buy the basic idea of the chain rule, just like what we just did before. See, so if I want to deal with dy dx, or say d dx of ln x or ln u, whichever you want to represent it, the rule says that, you see, this ln here, or natural log of a certain function, is the same as 1 over the function. Is that okay? And so all we are saying here is, I take the natural log of the function, and then I multiply it by the derivative of the inner function. And so we'll look at a typical example here. Now, supposing I have a function, say y equals the natural log of x squared plus 5 all squared, right? Now, I told you we'll buy the same idea of the chain rule. That's why I said the chain rule is an awesome rule in differentiation, because a lot of things that the other rules cannot do, the chain rule helps to make it very easy for you. So, just like we said, I look out for my inner function here. And so I will choose this. Well, not like I will choose this. This is your inner function. This is more like a composite function. This is a function on its own. This is a function. This is another function. So it's like a composition of functions put together. That's why we're referring to it as a composite function. This is my inner function. I kind of represent it with u, right? And once I have this, I can easily deal with what I have left, just like we did for the chain rule. So look at this. I say let my u be this entire function. Now I would want to find my du dx. Now I want to differentiate x with respect to, differentiate u with respect to x. Now look at this. This also looks just like what we just did before, a typical example of the chain rule. So here, what do? I take this, I bring it to the front, and then I reduce the power by 1, isn't it? I keep the inner function, I do nothing to it, and then I multiply by the derivative of the inner function, which is 2x. Now, if I differentiate x squared, I get 2x. This 5 is a constant, it goes away. Good. So this becomes my du dx. Now, I multiply it by 1 over u. Like I said, the natural log of a function is 1 over the function. Or let's say another way of writing a function that has this kind of expression is 1 over the function. And so if I say my u equals this, which is x squared plus 5 all squared, 1 over u is just going to be 1 over x squared plus 5 all squared. And I multiply that by the differential of that function, which I have done here as 2 into bracket x squared plus 5 multiplied by 2x. And so this is what I have done. This 1 over u, the 1 over u here, is the same thing here in actual sense, because the function wasn't given to us in u, it was given to you with respect to x. So this is the same expression. And then my du dx is this function. Right? And so 1 over this, well, you just, basic algebra. I can put this on top of this because it's multiplication. So this entire thing could become 2 into bracket x squared plus 5 times 2x, all divided by x squared plus 5 all squared. Now you can see there are some like terms, or some terms that really look like each other. And so this x squared plus 5 can cancel one of these terms. Remember, this is squared, isn't it? So this is the same as x squared plus 5 times x squared plus 5. So one of these terms will go away. Now what I'll have now will be just my 2 and then the 2x left. Okay, now 2 times 2x is 4x, and I'll be left with just this function. And so this becomes the final answer, 4x over x squared plus 5. And that makes it so easy. So you see the chain rule, we're going to keep using the chain rule in several instances. And you'll see it's just a little practice and you just master it. Identify your inner term, deal with it, and then multiply it by the outer term, and you're done. It's nothing extraordinary. Okay, now another one, another special function here is when we have something that looks like e to the power something. This e actually is a constant. It has its own expression here. But this guy is a funny, what's it called, function. The rule is, or a rule of thumb, no matter what you do to this function, e raised to the power something, it will be the same, right? This will not change its form. So even if you differentiate this, you see we had a function as this. When we finished differentiating, we ended up with something like this. If you have a function like this, if you differentiate, it will still be the same. So let's look at an example. Now, supposing that I have a function, say, e to the power x squared plus 1 squared. I have said that if you have e to something, it will remain the same. But here, this is kind of a composite function. I've told you e is a function on its own, and this x squared plus 1 all squared is another function. Then again, you see the idea of chain rule pops up again. So let's see how we'll deal with this one here. Now, in dealing with this, the rule says that just keep your e to the u. Now, it says that identify the inner function, just as we did for chain rule. You identify your inner function. This one, when you differentiate it, it will still be the same. Nothing will happen. So just keep that same function and multiply it by the differential of the inner function. So let's look at this. Now, e to the power x squared plus 1 all squared. This term here becomes my inner function, and this one becomes my outer function. So this one will remain the same. Now, I'll let my u be equal to this inner function, which is what I have here as x squared plus 1 all squared. Now, if I have x squared plus 1 all squared, that is again another composite function. It's a composition of functions. This is one function, this is another function. You can easily use the chain rule by now. I'm sure by now you are so bored with hearing the approach of the chain rule. But it doesn't hurt to go over it again. So if this is my function, I represent the inner one with, let's say, u, or I assume it's not there. So everything here, I assume, becomes u. Now, the moment I represent this with u, everything here becomes e to the power u. Very simple. But let's deal with this. So here, what I do is I deal with the outer function. I keep the inner function, and then I multiply with what? The differential of the inner function. And so here, 2, if I bring it to the front here, I'll reduce the power by 1. So this one becomes a power 1, so invincible. We don't necessarily have to write it here. So, and then I keep the inner function here, and then I multiply by the differential of the inner function. X squared plus 1, when differentiated, will become 2x. And so, like I said, e to whatever function at the top will remain the same. This is the same. You multiply by this, and that's your final answer, just as the rule is saying. Your e to the power u multiplied by the differential of the inner function, which is du dx, will be your final answer, and just as we have here. Okay, so like I also put before, I said we actually are not doing pure math. We are doing business mathematics. So let's see how we can incorporate this into some business perspective. And so let's look at the idea of elasticity. Now, basically, we know that elasticity measures the degree of responsiveness of a commodity. So supposing that I have a function, say, the demand function for a product, p squared minus 40p plus 400, where q is greater than 0. Of course, when we are talking of quantity, we can have a negative quantity. So our quantities must be absolute values, greater than 0. It says find A, the point elasticity of demand, and then determine the point elasticity of demand when P is 15. In fact, we can put this same idea of differentiation in general into whatever, whether economics or business perspective. The formula for finding the point elasticity of demand is, we normally say change in quantity over change in price multiplied by the price divided by the quantity. Good. Now, this change in quantity over change in price is the same thing as finding the slope. It's just like if you have the old price and then the current price, the old quantity is the same thing we're doing here. So this is the same as writing change in quantity over change in price, which is dq dp. Now, this is my quantity, the demand function. I'll differentiate this, and this entire function is the same as my dq dp, right? So let's take this and see. Now, if I differentiate p squared minus 40p plus 400, let's start from the easy one. P squared, this becomes 2p, isn't it? Now, minus 40p, this becomes 40. Then plus 400. 400 is a constant. It carries no variable. And so if you differentiate the constant, what happens to it? It goes away. So I end up having 2p minus 40. This portion makes up my dq dp. Now, let's look at the other portion. The other portion says, after you've found your change in quantity over the change in price, you multiply it by the price and then the quantity. What is our price? We were not given p in the first instance. So our p will still remain just as it's in the formula. But what about q? Q was given to us as a function, p squared minus 40p plus 400. put it here. So this function here is my dq dp, and this function here is my p over q. Now what do I have as my final answer? My final answer would now be, now I put this to the top, it's multiplication. Assume this has a denominator of 1, you just multiply and it goes straight forward. So now what I have is 2p squared. Now it is 2p squared because there is a p here, and if this p multiplies 2p, I have 2p squared. 40 times p will be 40p. So what I have now is 2p squared minus 40p, all divided by p squared minus 40p plus 400. And you're done. So this one here is the point elasticity. Now, supposing we know the value of p, now like the B portion of the question says, supposing p is 15, all we just have to do is put our p, or substitute it into what we found as our point elasticity equation, and we find what the elasticity value would be. Obviously, this is -6. Well, in fact, if wherever I see p, I put in 15, and then I do the computation. I have 15. So here, what you have is -6. Well, it's inelastic, and I know we can interpret this, but this negative sign is just telling us the negative relationship between price and quantity. And that's it. So that's how we are going to be applying this idea of differentiation in business mathematics and all these core structures and stuff. So we'll call it a day for this session now. So I'll meet you again in the second section.